This is the Amp Hour Podcast. Released June 3rd, 2025. Episode 689. Making the Invisible Visible with Sam Aldahar. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
Hello, and I'm Sam Aldahar, and I'm a power electronics engineer and a 3D graphics designer.
Welcome, Sam. How you doing?
I'm very well, thanks. Chris?
People probably know your amazing animations from LinkedIn and Twitter/X and other places, YouTube. And I have been a huge fan, just watching the invisible become visible with you and Blender and the tools you're creating. So thank you for doing that. It's very, very cool.
Thank you very much. It's my pleasure to be on your show today. Thank you.
Yeah. So where should we start? I mean, there's so much invisible in electronics.
Yes.
And you are making a lot of it very visible. I think one thing we should start with is that we are going to be trying to talk about a lot of things that Sam does make visible, but ultimately people are going to have to go click on links. I think that's really what it comes down to, right?
So, correct. Yes.
Yeah. If descriptions would have, been enough, then none of this would have been as cool as it is. So we will have links for everything, but people should be prepared to go click on them. Maybe we start with how you got started doing this sort of thing.
Yes. So I'm a full-time electronics engineer, and one thing I also like art. So I always say to people, if I did not become an engineer, I would have become an artist. So I will always enjoy drawing pictures, animations, and creating this sort of graphics. I've realized that us engineers, we do fantastic work. We build amazing products, great designs, but I think most of us struggle with how we present our work to other people. I think we always assume that everybody would understand immediately what we're trying to present. So I figured if I could sort of, I'm working on really exciting technologies, and I'd like to present them in a way. I'd like other people also to be excited as I am about it. And I thought if I could present it in a better way, in a more a realistic way, that would go a long way in helping people understand my work and selling my idea. So I started during lockdown basically to learn how to create digital art, 3D graphics, and my favorite tool is Blender to do all of this work, simply because it's open source, available for free, and lots of resources and tutorials online. And so that's how I started basically.
Not the easiest one, like I remember people were talking to me about it. I think as I was getting into 3D modeling, I was kind of asking questions online. People said, "Oh, well, Blender's another resource that's out there," but it was like, because I think the tool I was using at the time didn't have a great renderer, but Blender does, obviously. So you could like export a step file, put it into Blender, make it look much better, much more realistic, that sort of thing. What was that process?
And also
like picking that up and starting from like the I guess Blender has been improving as well, like many open source programs.
It has improved a lot over the years, and I've been using it for over 5-6 years now, and it was difficult at the very beginning, but I think the developers behind it, they've made enormous changes, and it's become very easier to learn than it was before, that's for sure.
And then like, what about the target audience for Blenders is still kind of the digital artist, animation, things like that? Or does it have a technical bent kind of in the direction you've been taking it?
So Blender, the target audience for Blender is just gamer, game designs, animations, cartoons. It was never engineering. I don't think there was a huge engineering audience for Blender. And so that's sort of where I thought, okay, well, there's a gap. I could now
smush it together.
Yes, exactly. Yeah. There you go.
Peanut butter and jelly. All right. I guess that's the US thing more. Oh, yeah. In the UK, they don't do as much peanut butter, I hear. So I don't know why, but
Marmite.
Marmite.
Have you tried Marmite?
I have tried Vegemite. I have not tried Marmite, but Vegemite is enough to scare me off that I'm like, I probably could leave Marmite behind. I think they're
it's either you love it or you hate it.
Yeah. I'll probably. You know what? I'll come to the UK. We'll hang out. I'll have some Marmite. How about that? Okay. So then what did it take to start doing this sort of thing? Like, what is maybe for people following along, uh,
Mhm.
and maybe thinking about doing this at home, what I
Right.
guess let's start with the good, like the good now, right? What is the best flow
Right.
method now, and then maybe we can talk about the, if it's relevant, what it was before.
So how to learn it. So
Yeah, like workflow of like you go from
work
3D CAD to there, or you start in Blender, or
right.
like where
Yeah.
what are the inputs and outputs?
So I think if you're designing a circuit board, a PCB, if you're using Altium or KiCad or any other tool,
Hmm.
you're sort of you already have that 3D capability there built in. So that's sort of where you might be able to start. Okay, you have a reference image,
Yes. Okay.
how it looks like in CAD. So you've got your circuit boards, you've got some cylinders which are capacitors, you've got some cubes which are resistors. So you have this sort of initial idea in your mind of how it might look like 3D
Okay.
wise, and then you use that as a reference to then recreate that in Blender.
Oh, really? Okay. So it's not like take
Yes.
a step file input. It's like start from scratch.
Yes, so unfortunately, Blender is not a CAD tool, so it
Yeah.
doesn't accept step files. It's a mesh tool. So basically,
Oh.
you've got points in space that you move around, and you create edges and planes. So that's sort of the first sort of hiccup that people will encounter is that, okay,
Let's
how
just say
do
people
I?
don't turn it off yet though.
Yeah,
There is hope.
no, no, no.
Yeah.
Exactly, and,
Yeah.
and that was the first issue that I encountered because
Mm.
I was expecting, yeah, okay, I've got my step files of components here and there, I can just drag and drop them in Blender. No,
Hmm.
it would not
Hmm.
accept it.
Okay.
You have to convert it to a mesh, so like STL files, OBJ files,
Okay. So maybe
that sort of
even like
stuff. Yes.
KiCad to FreeCAD to STL. Is that would that work or?
Actually, KiCad is one of the only tools out there that would export directly to Blender
Oh,
as a
really?
mesh file. So
Huh.
KiCad is fantastic.
All
Yeah. So
right. Yes.
in fact, people have actually created Blender add-ons
Uh-huh.
uh, which allow you to directly import your KiCad design on your project with the 3D models and have it exactly appear in Blender as it is.
Wow. All right.
So it's now
Open
possible
source.
to do that.
Open source.
Oh, there you go. Yes.
Yeah. Okay.
And then it's up to you to add the lighting effects and the
Yeah. Sure.
materials
Yeah.
and the shaders and everything else to
Okay.
it. Yes.
So maybe
Yeah.
we can define some terms. Well, actually, let's keep going with flow, and then I'd like to define some terms there as well.
Right.
Because yeah.
Yes.
Okay.
So yeah, as we said, you start from a reference image, and yes, if you might be able to import your, let's say you import your KiCad project into Blender because you can do it now, and then from there you can build on it. You can move objects, manipulate objects, you can add some lighting. It's all about the lighting. I've realized to make your animations and images look really good, it comes down to the lighting, and so you probably be spending a lot of time just getting that done right.
Mm,
And I
okay.
always struggled with the lighting and the shadows. Um, Also, materials. You need to spend some time to learn how to create the materials and the shaders because the basic CAD materials are very basic, either like simple colors.
Yeah.
But you can take that a step further. You can add some roughness to it, add some shine, add some dirt, add some surface imperfections
Got it.
to, that's you can then learn how to do these things. So
I mean, there are some other capable. So like past flows that I've used was like uh,
right.
KiCad to step into Fusion. Fusion, then you could also add material types, and I think it would probably be approximating the same methods of adding
Yes,
material properties, right?
exactly. Yeah.
Yeah. Okay.
Yeah. So that's sort of the process is, yeah, if
Okay.
you start in KiCad, export it to Blender, and then you could, and it's just simple as that. That's the whole process, really
And
straightforward.
and do you so you have these libraries of, I'm just looking at your YouTube channel again. We'll link all that stuff in. You have kind of these designs that you've worked on over
Hmm.
time. Do you kind of export just a cap and then use that cap over and over again, and then like just a QFN,
Right.
or do you do whole designs and then apply material types to each surface?
I started with sort of exporting, with CAD files, and then convert them to STLs and into Blender. So that's how I started. But then I've realized CAD is very perfect. CAD is too perfect. It's not really realistic. So then I actually, okay, I then make some changes. Like if I have a capacitor, I would import that as it is, but I would make changes to it such that it becomes a little bit more realistic.
Okay.
At so, but then ultimately I realized, you know what, I might just start from scratch and do the whole thing in Blender.
Yeah, right.
So
That would be like the
that's
maximum
how
control for each surface, each
maximum
thing, whatever.
control,
Yeah.
exactly.
Yeah, I
Yeah.
see.
So I've over the years I've built my own library of Blender created models, all
Yeah.
done in Blender.
Okay.
Um,
Yeah, I think it's probably going to come down to how much each person listening wants to try that. Like we probably should. We've
Absolutely,
already talked about
yes.
easy path is KiCad to Blender. That's great. So now you'd have a board that doesn't look as realistic as Sam's, but might be able to layer some of the interesting things on top of it.
Exactly,
To
and you can make some changes to it and modifications. That I think that might be but I would expect most people would go down that route because, yeah, it's if you've got something already there to work with and to make changes to.
Yeah. Okay. So then, before we get back to some of the terminology and stuff like that,
Hmm.
you obviously layer a lot of other interesting things on top of it as well. So things like magnetic fields. What's the tooling there?
Yes, right. Okay, so now we go a bit more, sort of a bit more advanced, a little bit more. We take a step further. So part of my research it was in wireless power and wireless charging, and that involves a lot of magnetic fields. And we we can't see those magnetic fields. We have solvers and simulation tools,
Yeah.
but then I thought, okay, I've got my board design, I've got my coils in Blender, they look great, but there's also something missing, which is the magnetic fields. I want to show those as well. So I first started by, okay, I've because I use other tools like professional tools to solve for magnetic fields. Like, for example, ANSYS is a famous one, CST, FEM2D is another tool. So then I thought I'd like to then export my simulation results from those tools and extract the data from those tools and put them into Blender and visualize them on top of my actual PCB design. So then the process for that actually is not straightforward, unfortunately,
Hmm.
because each solver has its own way of generating the data, how it stores the data, and exports it. So, for example, tools like I've recently used OpenEMS as an open source tool for antenna simulations, and that because it's OpenEMS, it uses sort of a industry standard or to store the results, and it's a VTK format, and so then you can then import that data into Blender via Python.
Okay.
So
A lot of glue
and for
code involved,
it's
huh? Yeah.
a lot of code. Yeah.
Yeah.
One nice thing about Blender is because it's got a Python console in it, so then you can if you know how to code a little bit, and so does KiCad, and so does OpenEMS. So then you can essentially link all those tools together with just Python code. And so that's how then I bring that data from all these solvers into Blender, where I then spend a bit more time to visualize them and add effects to them. So that's how I used to do things, and but then I realized, okay, well, maybe I can simplify this if I can do the whole simulation itself and the calculations within Blender.
Hmm.
I can do that. Why? Well, it runs Python. I can just run Python code for solvers. Um, and as you can see, and those screenshots there. And So I've started to create my own solvers within Blender to solve for the magnetic field. And it's very limited, of course. It's not the same level as the professional tools, but for sort of basic simulations and just to if you've got a number of ideas and concepts you'd like to try for designing coils, for example, you could use the Blender tool, which I released it. It's just called um, electromagnodes. You can use that to visualize magnetic fields and electric fields as well. It has its own limitations, but then once you have a design that you're happy with and you think you can take it a step further, you can perhaps then go back to your professional tool
Yeah. Well, I mean,
for it.
Do you charge for electromagnetic nodes or no?
It's electromag nodes. It's actually the free. It's free. It's for $1. You can get it for $1, and you can get it for free. I think on Gumroad. The reason why it's $1 because I can't set the cost to zero on these on these
Mm,
platforms.
yeah, that's no
So
problem.
that's why it's $1.
Yeah,
Yeah.
that's.
Um,
But I'm just comparing it with like HFSS and like ANSYS
right.
and like
Yeah.
just like
Yeah.
$1.
Yeah.
So like literally, if it's $1, you can have it's probably twenty
It's
thousand times more
obviously
expensive for the other ones at least.
absolutely.
Yeah,
Yeah, it's obviously not the same level as answers, and you
sure, sure.
probably will not get. But it's just like I said, for static magnetic
Yeah.
field calculations, electric field
I mean, I think
calculations,
right now for the
it does the
listening
job.
audience, I'm thinking about myself. Let's be really honest here.
Right.
I'm looking like, what is the lowest? Like, if I go to ANSYS and I'm like, hey, I just want to try it out, they're like, oh, sure, whatever, buddy. Be like,
Mm,
talk to our salesperson,
yes.
prove out your business case, and maybe we'll give you a 30-day license, and then you can figure out how ANSYS works. It's like, no, I literally just want to try it. This is the path. So that's great. That's
Yeah.
yeah.
Yes. I've also recently got some interest from a university in the US
Mhm.
where they're trying to now use electromagnet these tools to model stellarators in for nuclear fusion,
Wow.
which I found quite wow. This is quite something big for yeah.
Yeah. Well, they have big magnetic
It's
fields too, right? It's like
exactly, and
yeah,
it's all
many horsepower.
DC fields, so
Yeah.
static fields, and
Ah,
so the actual calculation is actually straightforward
cool.
for those.
Yeah.
Yeah.
That is very cool. Well, that actually brings back one thing that you and I were talking about before the show, which is just like, so, we've been talking about all this stuff. We're gonna get back to the technicals of how it's done. But just that this is so useful, like so useful as a student, as
Hmm.
someone who, as making the invisible visible. Like, I
Yes.
had so much trouble in school thinking about this stuff, and now being able to see it is so useful from a learning context.
Absolutely, yes, yeah. I've heard that as well from many other people as well. This, if we like we said, we wish we've had those tools back when we were studying,
Yeah,
and
yeah, yeah.
I wish that I had those tools too, and also that's one of the reasons why I also want to make this a bit more educational for people as well, just to get more people, you know, to like I said, to see to make the visible, to make the invisible visible, uh, and just to help them during their studies. Because I remember I think you said before the show is that yeah, like, okay, use the right hand rule
Yeah,
to
right.
visualize, imagine the magnetic field. Yeah, okay.
Right. Sure, buddy. Right. It's just like,
Yeah.
yeah. Can you maybe show me on screen? And
um
they're like, well, we can draw. Then they go on the board and they try and draw 3D, 3D on the chalkboard or whatever. And it's just like, yeah, nah,
yeah,
yeah, nah, yeah.
exactly. And also because now it's interactive. So okay, well, what if
Right.
I change my coil? What if the coil winding has
Yeah.
changed a little bit or have a turn here, and you can see the results straight away,
Right.
and
Right.
that really helps you understand what's going on, I think.
I think so
That
too.
that interaction. Yeah.
I think honestly one of the most so I think I've talked about on the show before, like one of the most useful things in my learning journey was actually sitting with analog engineers at Keithley and just them helping me
Mm,
develop intuition, right? It was like, okay, let's talk about some of the formulas, how they interact, how some of the, DID, V equals L d I dt, right? These kind of like mantras and like
yes.
building that sort of thing and just
Yes.
like being like, okay, well, the current is changing. So the voltage, you
Yes.
have inductance, you have current changing. What's going to happen? The voltage is going to change. Like that developing of intuition. This is kind of doing that same thing for RF and like short circuiting it because again, it is visible.
Absolutely.
It's like
Absolutely. Yes.
which
Absolutely.
direction,
Yeah.
which, how does it like, so one of your things here is like a human hand interacting with electromagnetic waves. Like ain't no formula that's telling me how to do that. Like you need a simulator in that
Abs-
case to make that happen.
exactly. Yeah. Yeah. Yeah, and yeah, so and that's why I love Blender as a tool because it helps you that to gain that intuition, to gain that understanding, and having a good visual to go with it really goes a long way. I
Yeah.
think
How do you know it's
with
right?
that.
Because so like I'm gonna look at your stuff, Sam, and I'm gonna be like, yeah, this is right.
Yes.
I don't know. you know. So like, how do you actually
Had
verify it? Like, how do you make sure it's actually correct?
For the that's a good question. So I actually do a comparison with like a professional tool. So I've been also using open source solvers such as Elmer,
Okay.
a finite element solver, Elmer, and so I kind of do a bit of comparison between the results that I get and with Elmer, and yeah, and then so if there's any limitations or differences, sort of I can go back and change things. So um,
Yeah, I think I
and
asked the same
sometimes I
question
do.
to Katerina when she
Yes.
was on the show. So she was on the show
Mm,
6, 7, 8, and she also does simulations of antennas and stuff like
mm,
that, and
hmm.
a lot of the same kind of stuff. And it's just like I don't, it's because it's invisible. I
Right. Yes.
yeah, you have to do it empirically, basically. At some point, you have to have some real world feedback.
Absolutely. The also I've been sort of relying on in some of my videos that I've been doing about calculating inductance of wire bonds and
Mm,
semiconductor packages. So
mm.
I've been sort of looking at what's being published online on papers and journals because they've done the measurements for their for their sort of package and their device, and they give you a number for inductance. And so, okay, I go back to my tool, like for example, the Blender, the Fast Henry tool that I've been working on.
Oh
I go
yeah.
back to, I
Okay.
go to, I use that tool, and then okay, I get a result, assuming I've managed to replicate the geometry, you know,
Yeah.
exactly to what was in the
Approximated, close
paper,
enough, sort of thing.
exactly.
Yeah.
Yeah, and then if my numbers are within the same ballpark, yeah.
And so Fast Henry is another tool that you have. So there's electromagnetodes and Fast Henry.
So Fast Henry actually is a tool that was developed in the perhaps late 80s, early 90s from MIT, an open source tool. And I think back then or the 90s, it used to be the industry sort of gold standard for simulating semiconductor packages, wire bonds, lead frames, inductors, coils, all of that. It's sort of now less over the past years hasn't been used a lot because simply it all comes down to how do you create the geometry to start with. That's what it comes down to with all these tools. It's just creating the geometry in an easy and procedural and flexible way, because the math behind all of these solvers is all the same.
Right, right,
It
right,
won't
right.
change. It's the same math,
Yeah. Right. I
but it
remember
comes down to
calculating
creating the
like
geometry.
resistor
Yeah,
geometry. I don't remember inductive.
yeah, yeah,
I remember resistors, just like the cross section and
yeah,
the
yeah.
length and that sort of thing. But then inductors, I'm not
Exactly.
so sure. But there's definitely physics
Yeah,
equations in there somewhere.
yeah.
Yeah.
And the equations, they're the same. It just comes down to, okay, what is the best tool to use to create the geometry?
Yeah.
And so I think that was one of the limitations why Fast Henry perhaps didn't,
Got it.
it's not very popular.
Got it.
And but
Just
it's a
to go
fantastic
back to
tool.
education again one more time.
Right. Yes.
Even
Yeah.
like when man, if a teacher could have been like, "Hey, we're going to talk about the geometric equations here that drive some of this stuff down the line." And then they could have shown me this and been like, "Sam does this. Sam does this in his program, right? You might want to do the same thing too.
Yes.
Look at all these things Sam has done and all the things you can do with it." Like just being able to draw that line back to it. Man, I would have paid so much more attention.
Oh, yeah, yeah, yeah,
Yeah.
yeah. No, it's actually quite cool. I also get some messages from back from my videos. Oh, like your videos have inspired us to do this and to do that,
Ah,
and
that's great.
it's really really nice to
Yeah.
hear that. Yeah,
Great, great. Well, hopefully more after this recording too. I
thank
think
you.
that's the other thing too. Is like people are going to keep finding this over time. It's like it's this cache of interesting things, and I mean, hopefully people are going to find it and be like, "Oh wow, Sam's even further along." And now like the Fast Henry tool is available, the electromagnodes is available, that sort of thing.
Yes.
So then Fast Henry is another Blender plugin, or how does that work?
It's a yeah, it's a Blender plugin, and it's so basically Fast Henry. The tool exists as a solver, but what I'm doing is integrating it within Blender because I want to use Blender's powerful capability to create geometry. And so I've realized, okay, I can create geometry Blender, but then I have to export it and to a text file and then call Fast Henry. How about I just use, well, Python again, back to Python. I've got Python and Blender. I might just run everything within Blender. So what happens is you create your geometry in Blender, you run Fast Henry within Blender, so it calls Fast Henry in the background. for
Hmm.
you,
Yeah.
and then the results are then displayed back within Blender. So it's a one single button solution,
Got it.
one
Got it.
push. Yeah,
So
I
Fast
forgot the
Henry's
phrase.
like a so like much like Spice by itself was like a Berkeley command line tool that like you had to put in all your net
Exactly,
names and stuff like that. But for me, it was useful when
exactly.
someone's like layering visual on top of it. And yeah, or and actually another thing I was thinking about with your the electromagnodes, you said it's simple, but like I still choose like Falstad simulator, which is like this,
Mm.
JavaScript applet,
Mm.
right? I don't need anything fancy because of the visualization. Like that's the part that's actually useful to me in a intuitive context.
The also the other reason why I sort of I wanted to integrate all of this is because I'm now actually using these tools in my full-time job to design coils, to design packages, and I want speed. I want to be able. If I've got a number of ideas, a number of concepts, so it's becoming Blender like essentially it's a 3D whiteboard
Huh.
where
Yeah.
you sketch your geometry. Okay, and then you can run a simulation quickly to see what the inductance is and the impedance look like. Okay, it's not quite what I want it to be, and then you make changes to geometry very quickly. You run that again. So it just speeds up that design workflow very quickly. And then, of course, once you've got a design that you're happy with, you might say, okay, then I can take this to a different tool, a more professional tool to
Got
continue.
it. Okay. Yeah. So this is the clay molding. This is the prototyping,
Exactly.
that sort of thing. Interesting.
Yes, exactly. Yeah.
Yeah. And then what are some of the tools that you will like so upon the, finding the 80, the Pareto 80% good enough kind of solution, then where do you take it to refine it? Just in your professional context.
Yeah, so I'm trying to move away from commercial tools and again back to open source tools, and I think they're becoming more powerful. So I'm now sort of experimenting with Elmer a little bit more. It's also an open source finite. It's an open source finite element solver, um, and so I'm trying to spend a bit more time experimenting with that. And
Oh, okay.
my plan in the future is to also integrate Elmer within Blender as well. So
Wow.
I think
Okay. Yeah.
that's sort of my next big project I'll be working on. But sort of that's sort of how my workflow is to then take it to another tool like Elmer, in some cases CST, in other cases ANSYS for a bit of thermal simulation. So
As much as I am a big fan of open source, like I get it that like a lot
mm,
of the, like someone's like comes to me and they're saying, oh, like, I want to use KiCad, but my company uses Altium, or we use whatever the other ones that are out there, and it's just like, but sometimes the other offerings that are part of it, or like you said, just the professional proven nature of it is that's what you're often paying for. It's like, no, this is like there are scientists
yes,
there proving this physics over and over and over again, and that's
yes.
and open source tools have caught up, which is great, but being able to go external is very useful and might be faster and a better solution despite the cost.
It is, yes, despite the cost, and because it kind of, I think people would trust them a bit more. I
Yeah.
think
Yeah.
they
Trust.
would
Yep.
trust the results a bit more from these professional tools, and obviously they spend, these companies spend a lot of time, investment, and money to make their tools sort of, not easy to, perhaps easy to use, but if you to minimize the mistakes and errors that a user could do when inputting the simulation data.
Yeah, and I think at
Whereas
the
with
end of the
open
day, we're
source,
we're
yeah,
really we're really replacing the true physical prototyping process because like you're going to prove it in a real world environment. You're going to build a prototype. You're going to put it into a chamber. You're going to do all this testing on it. And it's like, you know, even a $50,000 tool is cheaper than that, right? And so you're trying to like
yes,
just keep
exactly,
shortening that cycle over and over again.
yes, yeah,
And then so when you're doing these coils and stuff like that, you're also
mm.
validating, going through, kind of increasingly complex tools, but then you are also building physical prototypes and validating those on the bench.
Absolutely, yes.
Cool.
So yeah, we build the coils and we test them. We use the impedance analyzers, VNAs, and see how close our results. Interestingly, we always find, like, if we're building a coil for a wireless charging application, we always find that the inductance is pretty much correct to what we get in simulation,
Okay.
but the resistance of that coil is always off by factor of 2 or 3 times sometimes.
Really?
And yes, it turns well. It's actually a very because um, simulating and measuring power loss is actually very difficult, and getting that accurately calculated is very difficult. It comes down to the mesh, how fine your mesh is, and there's only a number of subdivisions you can make on the mesh before your laptop or your computer says,
Yeah.
"I've had enough."
Starts on fire. Yeah.
Yes, yeah,
Yeah. Or you go to
exactly.
like some super cluster and the cost isn't worth it, right? That sort of thing.
Yes, yeah,
Yeah.
exactly.
Okay.
Yeah,
2 to 2x though. That's higher than I would. But
yeah,
is it because it's a much lower resistance overall? Like in my mind, I'm like, oh, like 1 kilo ohm versus 2 kilo ohms, but maybe it's zero point 0.1 ohm versus zero point 0.2 ohms,
yes.
and so it's not that different in the physical sense.
It comes down to the difference between the how big is your inductance compared to the resistance. So it comes down to the quality factor. Uh, so the quality factor is frequency omega times inductance over R. If that number, frequency times inductance, is very high compared to the resistance, it's actually very difficult then to calculate the resistance accurately.
Mm.
Um, because yeah, it's because it says essentially it comes down to a numerical rounding error, I think.
Mm.
Um, when
Times
you have a such
all the mesh points as well, and like
yes,
how that kind of
exactly.
propagates through the system. Well, that is really, I mean, it's fascinating that you're able to, feed this stuff back, and like you're building your own tooling, which is
Hmm. Hmm.
incredibly cool. And yeah, and I think we're all benefiting, so that's really cool. How much does the RF stuff kind of play into it? So you mentioned the inductance stuff, all this stuff. You're also doing the Open EMS, and the some of the things I'm looking at on your YouTube channel are also like, we're up in the 60, 70 gigahertz. Like, wow,
Yes,
that's
yeah, yeah,
that's Open
yeah.
EMS at that point.
That is open, still open EMS. Yeah. So
Okay.
with this 60 and 70 gigahertz, that's just me pushing my sort of because I work in the low megahertz region in the hundreds of kilohertz, and I've always wanted to kind of explore, understand a bit more about 60 gigahertz, or well, as you go to RF and high frequencies, and just understand that a bit more. So I wanted to see how high I can push it,
Hmm.
and yeah, I can go to 70 gigahertz even more.
Yeah. Well, given Fourier stuff, I guess even
Mhm.
your
Yeah,
13.56 megahertz is probably has some
yeah,
gigahertz component. It's just very very very,
it
very
does.
small.
Yeah, 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 yeah,
Yeah, the way it goes. Okay, so we were talking about, to get back to the Blender stuff. So now we kind of talked about the different plugins you use, how you tie all this stuff together. Now let's, if we could get back to the shading and
right.
some of the technical know-how within Blender as well. Again, people probably have to try it out to really dig into it, but
As mentioned, is I think CAD is too perfect.
okay.
It's very clean, but that's not how the real world is. And though I always like to add something what I call surface imperfections. Like if you have your PCB, if you just built the PCB, yes, and it's come out of the assembly line, and maybe you've held it in your hand. Over time, it starts to build up smudges and dust collects on it and
Yep,
all of that.
yep, yep.
So I also wanted to capture that detail as
Oh,
well,
wow, really?
just
Okay.
to make it look, absolutely realistic in some way. So it was I did
You
that in my very early work, where I was just putting scratches and dust, and even in the air as well, floating particles and and all of that stuff. But yeah, creating the materials will it's not easy at the start, and you'll have to spend a bit of time experimenting with Blender's massive node system. So Blender uses nodes
okay.
to create the material. So you can add uh, lighting effects, you can add displacement, you can add bumps. So many things. It's massive. If you've ever used Simulink in MATLAB,
Yeah.
Simulink was very popular too. So Blend is a kind of a similar setup to that. If you think of it, it's a similar setup where you have these sort of blocks of um, either like you have an amplifier block or a transfer function block, and you sort of link all of these blocks together. So Blender is quite similar to that with its material system, where you have all of these individual nodes, that's what it's called, and they all have certain different functions, and sort of then you could link them all together and create the effect that you want for the materials.
Yeah, DaVinci Resolve kind of has that for their effect system as
Yes,
well.
exactly. Yeah,
Yeah.
very similar to
Okay.
that concept in DaVinci Resolve. So that's for the materials, and yes, you spend a lot of time trying to get the materials done right. As I mentioned, then it comes to the lighting. I think the lighting is really important, and that's where, because if you have a dark scene, no matter how much realistic your material is, it won't show up because there's no light on it. So you need to spend a bit of time on the lighting as well for it. And with Blender, there's different ways of doing the lighting. You can either insert like a point lamp, or you can insert a sun in your scene,
Oh, really?
or
Yeah, yeah.
yeah, all
I
of
have
that.
very crude controls of that in the KiCad
Yes.
simulator, but I really don't play with it. I just kind of like, all right, well, click on the more realistic thing, and that's the best I can do.
Yes. So yeah,
Got it.
I think KiCad has sort of like its on default setup of
Yeah,
lighting, where
yeah.
okay, this how.
Yeah, it's like 60
But yeah,
degrees above the plane, that sort of thing, and like,
exactly. Yeah,
yeah,
standard stuff.
it's
Um,
problematic sometimes because you it doesn't like the back of the board sometimes. It's like, okay, that's yeah.
yeah. One thing I've struggled with Blender is if you have objects that are sort of colors a bit dark and black, it's kind of difficult to make it appear
Okay, yeah.
look good. That's what I've struggled with, sort of the very dark colors. So what I've actually did the opposite. I've made my backgrounds dark, and so that all my PCBs are bright. And I've sort of, and you see all of my images. I only on my videos and images, you see all the background is usually dark, and the actual board, because that makes the your board stand out, your
Mhm.
design stand out a bit more, I
Yeah, and then
think.
you don't have to render the far field either, right? You don't have to, like, have,
Exactly.
a full
Yes.
desk
Yeah.
setup. It's like, "No, no, no, this is in the foreground," this sort of thing. Okay. How would you recommend people learn the lighting piece of it? Is it like, tutorials, or, do you have any tutorials and that sort of thing?
Yes. So actually, I've always been asked if you could make a tutorial, but then I would say there's a huge number of tutorials on the web about, and they do a far better job than me in explaining it. Well, my favorite tutorial is from a guy called Blender Guru. If you Guru, yeah, he does the famous Blender donut tutorial. Basically, how to make a realistic donut. If you're into
Okay.
donuts, how to make a realistic donut in Blender, and he goes through all the basic tools and functionality, how to, and the lighting and the materials and the nodes to do that. So that's what I would recommend for people to watch
Okay.
those videos. Yeah.
Okay, and I'm looking through yours here, and it looks like you have some about the stuff we talked about earlier, drawing components on PCBs, putting geometry nodes, that sort of thing. So you have some tutorials in that space, it seems like.
I've got some sort of just simple demonstrator videos on it. They don't go into the details of how I do it. It's just a matter of
Yeah, yeah, yeah.
finding the time
Lots of
really
time, right? Right.
to do that. Yeah. But one thing, Blender has got a very powerful system called geometry nodes, and that is, I think, one of the greatest additions to Blender. Allows you to create procedural objects and because Blender before that was a destructive design process where you would, okay, if you add in a cube in your scene and you change that cube size, that's it. You can't really go back to the
Oh,
original size.
got it.
And but now with geometry nodes, you can make things procedurally. So it's becoming a little bit like CAD, you could
Yeah,
say, but it's
yeah.
not really CAD, but it's procedural. And the lovely thing about procedural is that then you could create uh, design groups where then you could perform bigger functions because it's all procedural, and you just type in a number. Okay, I want to change the dimension the the IC's pin length, but I want you to change them for all pins, not just one pin. But at the same time, if I change the pin length, also make the IC body a bit bigger as well. And so you can sort of cascade all of these things. If you make one change, it cascades to bigger changes. Um,
And it sounds like that also makes it
Yes,
more scriptable as well. So when you're
more scriptable, and again, if you include Python with it within the mix, you just have a very powerful modeling capability.
when I hear Python these days too, with all the policies,
Yes,
I hear, hey, who's really good at Python? Not me. The LLMs are, and so like it feels like that, being able to lean on that sort of stuff too for when I get stuck in a corner, instead of like
yeah,
thinking like,
yeah.
oh, I wonder if Sam's available. It's like, no, no, I can ask a
Yeah,
robot.
and I've actually, because I've never really I've just recently started to learn how to code and write Python and other and C plus plus. I didn't know any of that, so I actually find like these tools, ChatGPT, they help me a lot to learn. I had to make changes to, like, I would not just take the code as it is and run it. Yes, although it would work, but I still want to make changes to it. I actually I found those tools very, very helpful in creating all my projects.
Awesome. What about so we talked a little bit on some of the lighting terminology you had mentioned as well. So like
Yes,
shader, like
yeah.
what is a shader?
The shader is how it is the part in Blender where it creates the material.
Oh, okay. So that's actually
That's
referring
called a
not
shader.
not
To
just to how
just
it
the
creates shade.
yeah,
It's just how it renders a surface,
the
that kind of
material.
thing.
Yeah, exactly. How it visualizes the surface, the colors, how the light reflects on it, if it's a metallic surface or not. So that's what is called the shader part of Blender. Yes, yeah. It might be a bit confusing because you might, oh, shadows.
Yeah, I
No,
was thinking
that's
shadows, and we were talking about lighting
yes,
and that sort of thing. Okay,
no,
yeah,
no,
because well,
yeah.
and also
So
like
yeah,
casting of light around objects too, right? So like we might have one smaller object in the shadow of another object. So then but maybe I don't have to think about that, which would be the best case scenario for me.
yeah. So sometimes, but the challenge I had, because with PCBs are very small, and especially with PCBs, if you've got like a big capacitor and you've got a tiny surface mount capacitor next to it or an IC, the shadow of that capacitor will not make those small components visible. So you might then have to add a second light source on the back to kind
Mm.
of put some light on these components. But if you put too much light, it starts to become too bright and too shiny. Oh, it's
Yeah, yeah, it's a lot of
yeah, it's
tweaking. It sounds like.
a lot of tweaking, and
Yeah.
I found some tools out there you could purchase. One of my favorite tools to speed up this workflow is hard ops.
OPS
It's
or DOS.
yeah, OPS, hard ops. Because with Blender, I think most people will find it hard to learn shortcuts and go through the menus and all of
Yeah,
that.
yeah, yeah.
But there's some add-ons out there that try to streamline this process a bit more and just simplify it for you. So, for example, instead of having to put many light sources in your scene manually, you could just use hard ops as a tool and say, please add 5 random light sources to my scene. Okay, it does it for you. Okay, if you don't like it, can you just randomly change that again? So
The
it
shuffle button, huh?
shuffle, exactly. It's the
Yeah,
shuffle button.
that's
Absolutely, it's a
great.
shuffle button. So there are tools out there to kind of speed up that workflow a little bit and
Cool.
make it less frustrating. Yes.
Yeah. Yeah, it does seem like, it's Blender seems like a tool that like, "Oh, you can build anything." And it's whoa, I wanna do, like, one thing. I want, like, the fastest path. Uh, yeah. Yeah, so that's great. That sounds like a really a useful tool. What about in so in a lot of these contexts, I'm just pulling up one of the ones that you have a meandered
Hmm.
inverted F antenna for far field, right? So now you've simulated this awesome. I think this is one of the first ones I saw from you. Um, what so now when we start thinking about like what's happening in over time, so now there's a time aspect as well. So how does that start working in here?
So that's where then, okay, I have my board in my scene, and I've got the camera, and you also have to decide at which point you want to move your camera close to the PCB to then start the animation of the electric field. So first of all, I wanted to show the entire board as it is from a distance, okay, and then I say to Blender, move in time 2 seconds forward, and then in those two, and then after those 2 seconds, move the camera close to the PCB and closer to the actual antenna.
Okay.
So I then tell Blender, okay, move 2 seconds in time forward, and then move the camera close to the board, and then I move the camera closer to the antenna itself, where I then start the animation for the wave. So I've already have the data in Blender, but then then I say, okay, once I get the camera close to the antenna, start playing that simulation data. So
Okay.
then and then I show a little bit more, and then I sort of zoom back a little bit to show then the entire simulation result.
Got it. So I'm going to say something that's very stupid now that should be obvious to people, but since I get to play the foil here on the Amp Hour, uh,
Yes.
often when I am rendering video for my own uses, I am reminded that a computer or that a video is simply 30 frames of still images per second, and
Yes.
I think that actually really helps me to kind of like then think about like, oh, well, we're moving through this video in time. I have it like playing in super slow mo here as Sam and I are watching a screen share, but like literally
Mhm.
it's just slices of time, and then it's like, oh yeah, like the the rendered visualization of an RF field is just you taking the slices of data, like the RF
Yes.
data that's overlaid on top of this, in addition to the 3D model, and then just taking pictures in time. Like that makes a lot of sense. Of course, right?
Yeah, of course, the waves, the electromagnetic waves, they're much faster than what the video shows. Because the video
Right.
shows the waves going, as they change within, with time. But obviously the waves are much faster than this. So yeah, as I said, it's basically snapshots in time, essentially.
Yeah, right. And then so then again, we're just going to describe the what we're looking at here. Obviously, an inverted F antenna is a PCB trace. The rest of the board X is kind of the other half of the dipole, right? But the
Yes.
we're looking then at kind of reds and blues and kind of these gradients that are there. Is
Yes.
that's the open EMS data? Like what is the reds and blues and RF kind of rendering here?
Right. Yes. So this video shows two sets of simulation data superimposed on. The first simulation result is you see how the meandered antenna lights up in different
hmm
areas.
Yeah, it
So
almost looks
that
like
is
little like
actually
blue dots almost, and like as it
yes.
changes there.
So
Okay.
these are the actual electric fields that is propagating along the antenna itself. And then those sort of gradients in space, these are then the radiated electric fields. And so the way I've done the color grading is that the closer you are the antenna, that's where you have the strongest electric field. And so it's dark and red, and then becomes really dark. So it's very strong. And then as you move away from it over distance, it decays and becomes lighter blue, lighter blue.
Got it.
Yes.
And that is the output of OpenEMS in this case, or is that something else?
That is the output of OpenES. It's actually the data size is massive.
I bet,
It's
yeah.
yeah, you're
It's
talking
probably
about
rendering all the
gigabytes of
data that's in
data.
there, right? Like, yeah.
Yeah,
Okay.
it is actually gigabytes of data,
Wow.
being visualized here. Of course, the way Blender does it is that every frame it then reads the simulation data for that specific frame, imports it into Blender, processes it, and then renders the result. And then as it does that, it moves to the next frame, imports the data, renders it, and does the result, the visualization.
So then do you have to like centralize so like OpenEMS I imagine doesn't care where it is kind of in space and time. So do you have
Hmm.
to say like, oh no, it's centered on this antenna here? Like how does it actually kind of physically correlate then?
And that's where I actually use Blender again to start with. So I actually create this antenna, and this PCB geometry was actually designed in Blender. So then I then I export Blender to OpenEMS. So then I've got
Aha. Okay. Yeah.
and then that means when I then read the results back, it's already sort of in the right position, let's say.
Aha. Yeah, that makes sense then. Yeah, that
Yeah,
okay.
yeah.
Yeah. Huh. Yeah, because you'd mentioned on the kind of the prototyping element of the inductive side of things with your power work. I would love to have, I've often thought about putting, these kind of antennas on boards, like inverted F, whatever. They're in KiCad at least, and I do 2.4 gigahertz stuff sometimes. But I'm always just like, I don't know what it's going to do. But I'd love to, like if there was some like fast and natural way to do this, and be like, oh look, I'm radiating from the wrong part of the board now because
Yes,
like that.
yeah,
If that workflow is there, I might feel more confident. I probably still wouldn't do it, but like, like that, the lack of it's all rules of thumb for me. And I'm just like, okay, well, I'm going to do my best shot and then hope for the best. But mostly because it's not going through production. If it was that sort of thing where it was destined for production and I had these kind of tools available, it's like, oh, maybe there's more that I would be willing to do. Okay, this is very 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 cool.
yeah.
Um,
It was a very fun project I worked on. Yeah, because like I said, I've been doing power electronics for most of my career, and just now getting into the RF world and being able to visualize all of these results really helps a lot. Helps me. And I was saying about the surface imperfection. So if you're
yeah,
viewing the video, you can see just next to the antenna, there's some smudges on the
I see
board.
that. Yeah, it looks like
There you go.
yeah, like flux stains and
Yeah,
stuff like it. Yeah,
flux stains. Yeah, which always is the case. I,
100%.
yeah.
Yeah, that's great. Wow, that is so cool. And yeah, I know I didn't notice when I was going through here as well. Like I saw some of the dots that you kind of have, like these little dots around
Yes,
dust
I'm
motes.
not sure about those. I was trying to kind of chat. Sometimes if you're in a room and you got a light source coming in, you see dust particles floating in space.
Yeah, yeah, yeah.
I was trying to replicate that, but I don't think it looks too shiny and too sparkly. But
It looks like the circuit is celebrating being
yeah, yeah, that I
simulated.
think if I were to do this again, I would definitely make some
I
changes
mean,
to that.
artists always think they would change their past work, but this is what 2 years ago. I mean, think about how far you've come in just in 2 years.
Yeah,
So like, yeah,
yeah, yeah.
that's wild, huh? Wow, that is really really cool. I mean, so what about just to stick on this example? So you have an inverted F antenna here, so that has an actual like copper element at the end. How does how does that actually go into OpenEMS? Again, like I having never used it,
Yes,
I don't actually get
right.
how this would kind of interact. Like if that was a ceramic antenna instead, what would have
Yes.
changed going into OpenEMS?
So for this particular design, basically you have the layout and you've got the geometry of the board. So you export that as a STL file
Okay.
with the copper layout, everything. So you export all of that into OpenEMS, and with OpenEMS, you say, okay, here's my STL file, okay, and then you have to define with OpenEMS. The difficulty with it is doing the meshing. You have to say, okay, please make my mesh dense in this location because that's where my antenna is. So you need to spend a bit of time doing that. But yeah, it's very it's and that's all there is to it. You just have to tell OpenEMS, here's my STL file, and here's where how the meshing I want it to be
Got it.
in this location.
Probably if my questions will be truly answered by going and trying it myself. So that's probably the best advice. But yeah, this is very, very cool. Let's look at some other ones. So you've also kind of gotten, like we mentioned, the up into the the gigahertz range. Does anything
Yes,
appreciably change in terms of the frequency that you are doing when this happens? Like, does that matter much, or is it again just another OpenEMS capability?
it doesn't really matter. I think you can go as high as you want, but always comes down to obviously if you go up in the frequencies, then that means you kind of need to make your geometry smaller and smaller, and you need to kind of have better control on the meshing that you do
Hmm.
for as you go up in frequencies, because as you go up in frequency, the wavelength is very small. You're talking about millimeters, and so then you have to sort of define your meshing within a millimeter or less of a resolution, like to get these sample points to be very, very close to each other. And so that's
Could
sort
you
of
define the meshing a little bit better? I guess I don't quite understand the
yeah.
meshing aspect. Again, it probably takes it for me to go and do it, but yeah.
Meshing is basically so how these solvers work is that okay, we have a geometry,
Mhm.
but we need to put in sample points. So sample points in space. So if I have, for example, a layout, okay, it's like a to D converter,
Okay.
analog to digital
Sure.
converter,
Yeah. Okay.
where
That's a good
if you
example.
got a sine wave,
Yeah.
if you put more sample points on it, then you can sort of almost replicate that sine wave,
Uh-huh.
right?
Okay. Yeah.
So, but if you have less number of sample points, you might end up with a square wave or something else.
Got it. Yeah. Right. 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 Yeah.
Yeah.
Nyquist and all that. Yeah.
Exactly. So it's a kind of a similar concept with meshing is that okay, you have to define the number of sample points in space. Now, in sample number of sample points in space to be able to kind of capture all the electric field everywhere. And of course, the more number of sample points you have, the more processing you need to do, and the more memory you need to do. And at some point, yeah, your machine would just say no.
Pass. Yeah.
Yeah.
Okay. Yeah, that's interesting. Yeah, just as another callback to the episode with Katerina too. I remember when she was talking about like I was confused about when she said talking about going into like an actual RF chamber, and I was like, well,
Right.
how do you measure all this stuff in the real world then? And she's like, well, no, you're measuring it at single points in time because that's all we can actually measure is like what is the reading at a single point in time in terms of power or frequency or whatever, or at a certain frequency, what is the power? So it sounds like maybe this is the similar way of you have many points in time and at
Yes.
different frequencies. And so you're saying simulate it here, simulate it here, simulate it here, and then kind of stick it all together, and
Yes.
then we can visualize.
Yes, exactly. Yeah. So
Okay.
in these videos, it's actually two separate simulations were done
Okay.
separately independent from each other. One simulation was just simulating the actual PCB layout, and then the other simulation is okay, um, measuring and calculating the electric field that has been radiated in space. So
Ah,
the two separate simulations, but yeah, I just put them all together for one full visualization.
very cool. Yeah. I mean, even just how you have the sample 60 gigahertz
Yes.
square. Like I know that those are like filters and that they have some impact on.
Black magic
Yeah,
voodoo
they're
stuff.
yeah,
Yeah.
exactly. It's just like I know there's physics in there somewhere. What I
Yeah.
really think about though is like, okay, but if I actually wanted to implement this myself, there is zero intuition on my part. It just squares on a page, and it has some impact, but I don't know. I don't get
Yeah. Yeah.
it.
Yeah, so yeah, you definitely need a tool like this to actually you understand. Okay, the waves are being generated from the circuit, from the integrated circuit. Okay, and they're traveling along this transmission line, but then they're hitting a stub along the way, and then what happens is that okay, when one wave reflects back, some continue, some reflect back, and yeah, it's just being able to visualize that and seeing it just goes along. It just helps you so much. It's otherwise you're just relying on equations and graphs and charts. And
Yeah.
okay, yeah,
Yep. Yep.
yeah,
Exactly. Well, and you also have one where you put a hand in there too.
that's my favorite. That's one of my favorite one. And if you notice in the video at the beginning, the tattoos I put on the hand,
Yeah, let's see. Tattoos on the hand.
or the
Volt.
so this is something in Blender you can actually sculpt. So imagine like in the real world you've got a sculpture made of like clay or stone, and you can sort of massage it and move things, and you can draw on it and you can paint on it. So same thing with Blender. It's actually a hand that I got. I just got this model from somewhere on the web, and I've sort of had to change the fingers and point them and so I wanted your index finger to be straight up and all the other fingers go down. And I said, okay, I'm going to put a bit of something interesting because I was listening to Black Sabbath, Ozzy Osbourne, and I remembered he's got tattoos on his knuckles. So I thought I'd do the same thing.
Nice. I like it. Yeah, that's great.
And I also put because I put a bit of hair as well on
I
because
did notice that. Yeah.
I was looking at my hand. Okay, I've got some hair on my fingers, so I
Yeah.
might just put that as well.
Make it more real. Yeah, and actually, what
Make
I'm
it
really
more.
noticing about this is you also added surface textures to make it like more shiny, like a human skin. It seems
Yes,
like. So
exactly. Yes, yeah.
yeah.
Perhaps I need to do a bit more work on that to make it a bit more realistic because it's still it's still a bit too shiny. But yeah, I didn't want to
It's
spend too
like
much
someone had
time.
just gone to the salon. They had some skin
Yeah,
treatment, that sort of thing.
yeah,
Yeah. Okay.
exactly. At
So
least the fingernails are good,
Yeah,
and
exactly. Yeah, the manicure was
yeah.
done. Yeah, yeah.
So there, then in this one, actually, yeah, okay. So there's two simulations, and you can see at some point during the video where I switch to the simulation of the field that's been generated, and then that goes up to how the waves interact with a human hand and a finger, for example, and you see
Oh,
some waves bouncing off and some waves traveling along the surface,
uh-huh.
and
Yeah, it's showing almost like a waterfall plot in 3D space to show the interactivity. Yeah, because I mean that's another thing where I have a I think a 26 gigahertz or like one of the low cost sensors that's out there, and it's
yeah,
like, oh yeah, we can read your heartbeat from across the room now.
yeah, yeah,
excuse,
yeah.
excuse me, like what? But I guess it's just but detecting little vibrations in space and then back calculating, saying,
Yeah,
oh, probably a
exactly
human over there.
because
Yeah.
yeah, because you're working, your wavelength is in the millimeter range, so you can now detect all of these small, very very small changes in the surface.
Mm.
Uh,
It's just amazing to me how does anything work, Sam? That's what I'm really getting at. Like,
it
it's just amazing.
was a fun project. I really enjoyed working on this one.
Do
Yeah.
do you do this similar kind of work then for so like your magnetic sorry your power charging stuff? Do you also
Yes.
simulate humans kind of in the loop as well because of how it might impact you know
Yes.
that,
So for sort of wireless charging and wireless power, it's a much lower frequency. We're talking about anywhere between 100, 200 kilohertz to a few megahertz, low megahertz region. And so obviously in that scenario, the wavelength is very, very big. And so it's because it's more of a near field sort of simulations you do. But then what's important is to do SAR simulations, specific absorption rate. uh, you basically want to show if actually if a human gets too close to your wireless power coils, how much heat do you generate in human tissue?
oh,
And
okay.
there's certain limitations and guidance about how much energy you can deposit in a human
Hmm.
uh, limb or body.
And do you deposit heat into humans? That'd be a bad thing, right?
It'd be it'd be a bad thing. Actually, as a matter of fact, in like your smartphone, when you put it close to your ear, so companies they do SAR simulations
Uh-huh.
and they measure how much energy they're depositing in your head, in your ear, um, and sort of this is what these professional tools allow you to do. Very, very, very good is that you can insert a human limb or head or hand, and you can put your phone or your energy, your source generator close to that and measure how much energy you're depositing. So I think you're allowed to deposit 2 watts per cubic centimeter, I believe, no more than that over a 6 minute period.
Hmm.
There are complicated regulations and
Yeah,
standards
yeah,
around that. Yeah, yeah,
yeah, and that's where all the crazies think that we're being
yeah.
impacted by our phones, but it's non-ionizing radiation.
Yes,
So yeah,
exactly. Yeah,
that's the thing,
absolutely.
folks.
Yeah, yeah.
Yeah. Well, just going up your other stuff here as well. You have some PCB motors. That's super cool as well. That
Yes.
kind of comes.
So this is a collaboration with Carl. Carl, he does.
Oh yeah, past
Um,
guest of the show, Carl Bugeja. Yeah,
yes, yeah,
yeah.
he was on the show, and he designs these PCB motors with PCB coils, which was really 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 cool stuff he does. I'm a
Mhm.
big fan of him, and I thought, okay, this is a perfect application for my tools. So okay, he's got his designs available on GitHub, so I can download them and I can put them in Blender. I can do my surface imperfections and all of that, and lighting, and add other objects to the scene, and then okay, I can show the motor spinning, and I can show also the magnetic field that is being generated by the PCB coils that he has
Mm,
in there,
yeah.
and visual and make all of that as a one visualization. So okay, first of all, I'm showcasing the board, and then I get close to the actual, you know, point of interest, which is the motor. Okay, the motor is spinning, um, and then okay, the motor then you can see the screws come apart, and it leaves the scene, exits the scene at some point,
Hmm.
and then that then shows the PCB coils which he's designed, and then I use my electromag tools to in Blender to actually visualize the magnetic field lines that are being generated by one coil.
Yeah, this is now switching to the magnetic domain. Obviously, lower frequency, that sort of thing.
Yes.
how much when I guess when do you switch over from the power mag?
Hmm.
Sorry, the one to the other. I forget the name of the. Sorry.
Yeah, switch from electromagnodes or from a near field sort of simulation to a far field simulation. It depends on who you ask. Everybody has different. I would have a different answer, I would say. But in my case, it would be anywhere above 100 megahertz, I would say.
Okay, that's a
Mm.
good general guidance. I guess it's also what you care about too, right? If you care about like the actual like magnetic attraction of a coil might be different than or like power delivery from a coil, which is probably in the similar sphere versus the interference effect. You could probably still use it to see how this might interfere with your, if you had a radio
Absolutely.
nearby, but
Blender sort of is the hub, it's the central hub, for
yeah.
creating geometry, for visualizing results, trying
Mhm.
quick concepts, and just tying everything together, I would
Totally.
say.
Yeah, I'd say
Yeah.
just to back to the education sphere as well, like just the interaction, like, oh, okay, perpendicular fields, electric and magnetic fields are perpendicular, blah blah blah. It's just like, uh, what? What do you mean?
Yeah.
Like, and then they go up to the board and they start holding their hands up again, and they, drawing X's and O's into the board. But man, just this like, I mean, first off, this is just cool by itself. Like seeing, this is like, watching how Hollywood, you know,
Yeah.
renders this stuff as well. That might be my go-to, but this is an actual like modifiable and demonstrable thing that I could do potentially as well.
Yeah.
Like that's
Yeah.
that's where it really starts to come together.
Exactly. Yeah. You can modify it. It's interactive, as I said. So if you make a quick change, you see the result immediately
Hmm.
change. And yeah, I mean, it's all because we've got powerful computers these days and very fast processors, GPUs. So
Yeah,
you know,
yeah, and you have
pretty much.
units on here as well. So like just to take it back to
Ah,
the electronic, sorry, the inductance stuff. How does that tie
yes.
back in where you actually are calculating values here?
That's where I'm now using Blender's geometry node system. So, like I said, it's like almost like Simulink, where I've actually done my own inductance calculator. So it's Blender is calculating the inductance of this coil within Blender itself. It's not using any external tools. The calculation is done internally. Um, and like if you know the math behind it, and Biot-Savart's law and all of that, you could sort of program all of those equations in Blender, and you could just do a quick calculation of the inductance. And I've verified it's actually correct.
Yeah, 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 yeah. Wow, that is, and that's
Yeah,
and that's the kind of stuff you said you're doing professionally every day anyways. So like it makes sense that you would.
yeah.
Does it change with like imposed voltages and stuff like that? Like it's showing it ticking up here, but
Yeah, because the way it's calculating it is actually it scans the magnetic field over a certain area, so it's scanning it and it's going to go up and up until, but at some point it will stop. Like that increase will then stop increasing anymore. So um, it because sort of I'm using air core coils, so I'm not using ferrite material or other nonlinear material. So you could say the inductance is almost linear with voltage and current, and pretty much
mm,
stays constant.
got
If
it.
I were to have ferrite material, then yeah, it becomes a more complicated calculation.
Got it. Okay. Oh, and you have a whole video on inductance calculation.
Yeah,
We'll put that into.
yeah, yeah.
Okay, great, great. I'm just dropping links in my notes here as we go along, so
Mm,
this is good. Yeah. Okay. Wow, that is, and actually, this is nice too. The thing that I like about this is that this calculating inductance, it's actually showing your whole screen. So as it's actually showing you working in Blender, which is really cool
yes,
because
yeah.
because I haven't tried it yet. It's still kind of unknown to me, but that's really really important to be able to
Yeah,
look at.
I've realized that it's I get more interest in in me actually showing how I use Blender and how
Mhm.
I'm navigating around it instead of just showing the actual result itself. So I think I found that people like that more, just showing your workflow and what is it you're
Yes,
doing within
totally.
Blender.
Yes. Yeah, I
Yeah,
mean, because I can go to your GitHub page and we'll put in the
see
various
it all there. Yeah,
yeah, the fast Henry tools, the electromagnode tools, all those. But it's different than actually seeing it happen, right? That the
yes,
ability to be like, oh, I could go pause it if I need to and see what Sam's doing on his screen, like the where do I click kind of piece of it all is also very
yes,
important.
exactly. Yeah.
So yeah, that's really. We will link in your YouTube channel. We will link in
Mhm.
your ArtStation channel, which is another place you kind of highlight the the
Yes.
the videos and the gifs of this sort of stuff that ends up on social. What else should people check out from your work? I mean, where?
I think just showcasing products. So recently, the last one is I did this smartwatch. If you the first video on arts, yeah, that one. There's ZS Watch, open source smartwatch. So this is an open source project, and people they're doing your own smartwatch. It's a KiCad project, and I thought, okay, well, I could experiment with that because I was trying to experiment with creating animations of how components of fall on a PCB. Like sometimes you see these product demonstrations from Apple, Samsung, Nvidia, where they show how the components fall on a PCB and how everything is assembled and how it all comes together. So I was trying to kind of experiment with that a bit more, and because all these animations of all these objects coming together, it's all actually programmable and scripted, and so it's not me moving things manually with my with my mouse cursor. No,
Uh,
I'm actually programming it all.
oh, interesting. Yeah, I mean that's very
Mhm.
useful. I mean, I can imagine every Kickstarter campaign in the world wants this sort of with electronics would
Yes.
want this sort of thing.
Yeah.
Yeah, I mean, exploded views are always fun, and now this is like it's like an
Yeah.
inverse exploded view, which is great.
Yeah.
I shouldn't dig through every single video that's here. That is for the audience to do. But man, I want
Yes.
to. That's very very cool. One last thing I wanted to if a person listening wanted to fast track their learning, what is your
Yes.
recommendation for the fastest way to get started doing this sort of thing?
Fast way is to start to learn to get to know how to use Blender, to get to understand how to work within Blender, how to move objects, how to manipulate things. I think, and the best way to do that is just to go watch a YouTube tutorial from Blender Guru. I think that's the quickest and fastest way. It's probably spend about 3 hours on it. You'll be able to know how to get around Blender, how to do basic effects, shading effects, and all of that. So, oh,
Okay, so
that's the
first
first thing I would
step
say.
one is build a donut. It sounds like.
Build a donut.
Yeah. Okay.
Absolutely.
Okay.
Build your Blender donut. You could spend a day on it, but that just covers everything. And then after that, okay, like I said, start from a reference design. So perhaps if you're into electronics, you're doing PCB, get your KiCad project, your 3D board into Blender straight
Okay.
away.
Yep.
Do that,
Okay.
and then that at least that gives you something to work with.
So find a KiCad design on. If you don't have one your own, go find one. Start in
Go
KiCad,
find one.
and then use the Blender importer. Sounds like.
Blender, yeah, you can export it. As a Blender KiCad add-on. You can download it; it's free, and you can just get your project into Blender. And from there, at least you've got something you can work with. You can manipulate. You can make changes, add lighting, material, and I think that is the best way, just to able to use Blender. And then you can take it a step further by going into geometry nodes, into procedural modeling, into then a bit of coding, and then sort of getting actual simulation data into Blender and all of that. So three steps, yeah, I would say. Donut, reference design, and then go take it to the next step with geometry nodes.
Okay. What about when should people pull Fast Henry and the electromagnodes in? Like, should they? Is that a suitable third step, or should they do the geometries first?
I would say that would be as a third step, definitely. I think as a third step because yeah, those tools, Electromagnet Nodes and Blender Fast Henry, I'm assuming that the user already knows their way around Blender, knows how to access things, knows how to edit things. So yeah, I would recommend in sort of step number three.
I'm really asking for myself. If it wasn't clear, I am very selfish, and I already have. I don't know how to use Blender yet, so that's definitely the first step. I have a KiCad design. I could pull that in. I can share mine if people don't have one. I have some open source hardware, but there's lots of open source hardware in KiCad, which is great.
And if people have any questions or any comments, you can find me on social and just send a message and post a message somewhere, and I'll try to help us as much as I can.
Okay, great. That's how we always end. So
Yeah,
LinkedIn, Twitter/X. Where should people find you?
everywhere. If you search my name, you can find me. I think my two most active places are recently have been LinkedIn and X. You can find me on those two platforms. You can find me on YouTube as well. So yeah, just those three sort of platforms that I'm currently very active on. Also, you can post on the EEV blog forum as well. I've got a
Ah,
few posts on there.
okay, great.
Yeah,
Well, Sam, it has been an absolute pleasure talking to you.
likewise.
I really enjoyed I mean, up until this point, I've just loved looking at this stuff on different platforms. But now, you opening up the educational aspect of it too is going to be really
Yeah,
enabling, I think, for a lot of folks. So thank you for being here, and thanks for your tools.
thank you very much. It's my pleasure to be on the show. Thank you very much, Chris.